So today's going to be a little bit different. This is going to be a three-part problem with each part being kind of related to each other, but also being slightly different from each other. They do all have to relate to the fluid equation, the continuity equation specifically, which you can see over here. But each of them touches on a different point, which I believe will be pretty helpful. So the first one is to ask, okay, show that the fluid PDE is conservative. By that, the question goes like this. So consider the continuity equation here at the top. Define big N such that it is basically the integral of all of the N. So it's going to be just the whole fluid itself, where the volume has boundaries that move with velocity v. So show that the full derivative of big N is 0, so that basically it doesn't change. In this, this is also called the conservative form. So solving for this, we will use v without any arrows on the top as volume, and v with arrows on the top as the velocity. So the goal here is to prove that n does not change. To show this, let's take n and let's take the full derivative of it. And you can break this up into two parts. You can break this first into the partial derivative of time within the integral, and then the partial derivative of the integral. So this is called Leibniz integral rule. I wasn't too aware of this until recently, and this would be very helpful for any kind of problems dealing with full integrals of a function that's inside a derivative. So taking the integral of the first term, since dt is already inside the integral, we could look for any special relationships. For this one, we were given this equation here. So you can just substitute this into here, and then you're going to end up with this. How do you get from this to this? So this is a volume term. So this is an integral over volume of n times v. Knowing this, v, or the velocity, is not dependent on x. So you can take v out. This is a special case in physics, any physics problem, where v is independent of x, because there's always going to be kind of 7 dimensions that are conserved within this thing called phase space, which is v, x, and t. So all of these are independent of each other. X, v. Actually, I'll just say x and v are independent. For a lot of special reasons. If you do any classes dealing with analytical mechanics, talking about the Lagrangian, Hamiltonian, that kind of stuff, then they'll teach you why this is the case. But for now, we can just say, okay, yeah, v doesn't depend on x. So because of that, we can take the v out of the integral, or out of the whole integral term. And we notice that this is basically negative gradient of n with a volume derivative. And what does this look like? Well, this is simply the Gauss's integral rule, which means that this can turn into a surface integral. So just simply turn that into integral of s, or I'll just take the negative out, of n ds. So that's how this transformation is done. Okay, so after that, we want to take the second derivative, or the second integral for this term. So over here, we have 1 over dt integral v n d3x. We can see that the differential term, this is integrating over a differential term, meaning that this is looking at the change in the surface. So if this is looking at the change in the surface, then this is actually integrating over the surface and then putting a change term over it. And over here, then the dt's on the outside and the inside will cancel, leaving you with this term, which is nds dot v. And this is exactly the same as 1. So if you have the first term and the second term, they'll add up to 0. And you just proved that dn over dt is 0. Okay. So this is the first part showing how dn dt is conserved, or how n is conserved over time. The second part is to show how how we could write this equation in terms of a kind of a singular value, or in a sense reparametrizing it in a constant divergent flow. So what does this mean? The question here says, consider the partial differential equation, of course, the continuity equation again, with an initial condition u of x at t equals 0. So this is what we're trying to look for. We're trying to look for what the initial what the not just initial condition is, but what u is based off of the initial condition that t is 0. So over here, kind of a picture form is like, let's say you have like a vector field, right? Or kind of a field that you want to work off of. There's so many different ways you could go about doing this, but we can instead of approaching this by looking at, okay, we start at like 0 and then seeing how this follows the curve. We can take another approach and say, okay, let's start along a curve and then see how this changes. So in this case, the curve that we're starting along is going to be t. And if we just notice from this, we can also notice that the change in u, or the change in this this constant here, is going to be 0, because this equation actually came from the fact that du over dt equals 0, which is the how the whole continuity equation was derived. So let's start from that assumption, which du over dt equals 0. Then we can see that dt over dt equals 1. Here we're just choosing an arbitrary t such that this happens. So differential wise, they're the same. But then, of course, if you take the integral, t is going to be t. I'll say tau actually. T is going to be tau plus c. And then du over d tau is 0 as defined. So u is a constant. And then dx d tau is going to be v. Why is that? Well, because time derivative of x is going to be v. So over here, then you know that this is going to be alpha x. Now, since this is dx d tau equals alpha x, then we can solve the differential equation for this and then turn it into an exponential and plug in t plus c, which means that the initial term is going to be x0 e to the alpha c. But since x0 is arbitrary and e to the alpha c is also arbitrary, then you can just merge the two terms together back into x0. And then you end up with x0 e to the alpha t. So when we want to look at the u over here, it says u equals u0 to the x term. This is looking at how u changes according to u0. So at u0, t is going to be 0, but that means x is going to be x e to the negative alpha t. So we're going to look at u equals u0 of x0, which is going to be x to the e negative alpha t, and that's going to be the answer for the reparametrization. So now that we have this reparametrization, we can continue on to the last part, which is asking about, okay, let's say you follow one of these curves, like over here, and by following one of these curves, you have a fluid, right? But you'll notice that all the fluid kind of like disappears over time or goes away. This is because the divergence of the fluid, or kind of the outflow, is going to always like leave. So over time, it's going to dissipate, and because of that, there's a divergence term. So we don't have to prove that the continuity is -3 alpha n, but it does help to show why that is. So if you look at the divergence over here, this is going to be delta times v n. That's also the same as d dx of v, right? Or not d dx, d vx of vx plus d vy of vy plus dot dot dot, which equals 1 plus 1 plus 1, which equals 3. So that's how you get the 3 from here. Okay, so from that, since we are following the curve n0 of x e to the negative alpha t from which we got from above, then we can add an exponential decay term and then kind of guess what the exponential decay is. Because let's just say like we're following this one curve, right? Over time, let's say there's like some fluid clump here. Over time, it's gonna just leave and then leave like this. This whole term is going to be same, right? The same, like how we're following this term. So it's not gonna be, in a sense, changing, or the fluid's not gonna be like moving like here, because if it is, then we're gonna renormalize to this side. Instead, what we're going to see, the kind of difference that we're going to see, is that this is going to move out. We're just going to see how this spreads out. And that line that we're following doesn't track how this spreads out. So we just need a term to see how this spreads out. So let's just add in n equals q x of t, which could be an arbitrary q again. And then we just multiply that and apply this to the continuity equation. Then from here, it kind of becomes obvious that, okay, if we want these two to equal something that's of substance or easier to solve, we can simply take out the x dependence of q, because q is something we made up. So q xt equals q of t. This is just something that we made up, so we could set whatever parameters we want. And then we notice that, okay, if this is q of t, then the gradient value of here, of q, is, what is it? That just goes to 0, because q has no x dependence. And then it becomes obvious that qx of t can be qt, so that the time derivative of q is -3 alpha qt. And that simply makes q e to the -3 alpha t. So combining that back again with the original, we get n equals e to the -3 alpha t times n0 x times e to the -alpha t.